Forgot to make myself a copy. Whiteboard. Okay. Okay, so today I'm going to talk about how we deal with situations when we have complex eigenvalues. So let's just jump right in. An example of a situation where we have complex eigenvalues: x prime, -1/2, 1, -1, -1/2 x. So we're looking for solutions to this system of differential equations, or vector valued differential equation, if you want to think about it. All right, so first step is finding the eigenvalues of this matrix. So I'll form the matrix. Let's call this A minus Ri, going to be -1/2 minus R, 1, -1, -1/2 minus R. So this is equal to -1/2 minus R squared, which is just 1/2 plus R squared, plus 1. So this is R squared plus R plus 1/4 plus 1. So that's 5/4. Equals 0. And let's see, what do we get for roots of this? So I'll just go ahead and use the quadratic formula. So minus b plus or minus square root of b squared minus 4ac. That's 5 divided by 2a. So I get -1/2 plus or minus square root of -2. Right, that is 2i. Oh, sorry, divided by 2. So plus or minus. So I get one root as -1/2 plus I, and the other root as -1/2 minus I, right? And you'll notice that, well, maybe I didn't introduce this term, but suppose we have a complex number a plus bi, then there's an associated complex number a minus bi, which is called its conjugate. So these are just pairs of complex numbers that are associated to each other. If we look at them on the complex plane, then we have a plus bi here, then a minus bi is this reflection across the real axis. So if we take take this complex plane and flip it around the real axis, then everything gets switched with its conjugate. Now, this is just a fact that you've probably seen before. The complex roots of a polynomial with real coefficients always appear in conjugate pairs. So you saw we had a polynomial here with real roots. And in this case, it's a quadratic, so it will always have exactly 2 roots up to multiplicity. So we have our 2 roots here, and in fact, they appear as conjugate pairs. Now, that means these are our 2 eigenvalues, the 2 eigenvalues of the matrix. We have 2 distinct eigenvalues, no longer real though, but we can find the eigenvectors. So let's go with the eigenvalue -1/2 plus I and figure out what a corresponding eigenvector would be. So we have our matrix as -1/2 minus R, so that's plus 1/2 plus, sorry, minus I, should be minus I. -1, 1, and -1/2 minus -1/2 minus I. So what we get from this is the matrix -I, -1, 1, -I. And just like before, we can find the non-trivial vectors that we can multiply by this matrix to get the vector 0, 0. Nothing has changed in the process of what we're doing here. We're just using complex numbers instead of real numbers. So if well, first of all, maybe I will take a second to say, we're expecting this matrix to not have linearly independent rows. And in fact, that is the case. If we take this row and multiply it by -I, we see we get this -I here. And then if we multiply -I by -I, that's just I times I, which is -1. So we see that only one of these conditions that we would get from a system of linear equations is relevant to figuring out what our eigenvector will be. So if I use A1, A2 for the components of the eigenvector, then I get -I times A1. Actually, I'll just write it out. So this is the matrix vector equation that we're trying to solve. This times some vector, some unknown vector that I'll just call A1, A2 is equal to 0, 0. And the system of equations that I get is -I A1 plus A2 is equal to 0, and -A1 minus I A2 is equal to 0. And of course, just like we showed a second ago, the second equation is just a rewriting of the first equation. We're just multiplying both sides by -I. So it doesn't change the things that satisfy that equation. Now we've got an equation and 2 unknowns, a single equation, essentially, because one is just a rewriting of the other. And so we're going to have one arbitrary variable, and then the other one will be determined in terms of it. So if I rewrite this one, I get I times A1 equals A2. I'm just adding I A1 over to the other side. And so I can choose A1 to be 1, and then A2 is I. So my vector will be, I'll write it over here next to the eigenvalue. 1 I. Highlight this so we don't lose it. Okay. Now the other eigenvalue is -1/2 minus I. And we'll go through the same process. We'll get the matrix I, 1, minus 1, I. Right? And if we work out what the system of equations is from this, if you watch the video from yesterday, you'll see that I had been sort of kind of I'm not writing out every single one of these steps. So I don't know what my point was with that, but anyway, I'll use the second one here, minus A2 plus minus A1 plus IA2 is equal to 0, so that it's easy for me to just say A1 is equal to IA2. So in this case, I will get A2, I'll treat A2 as arbitrary and A1 is determined in terms of it, so I get I1. So this is my other eigenpair, pair of an eigenvalue and an eigenvector. And so I get my general solution from this. X of t is equal to C1 times 1I. Let me write that a little more legible. 1I e to the minus 1/2 plus I t plus C2 I1 e to the minus 1/2 minus I t. Right? Did I mix that up? I went off my notes for a second. I must have messed something up here. Sorry, just give me 1 second. Oh no, I didn't mess anything up. The point that I wanted to make, and I kind of was a little too clever for myself. We can pick, remember that any scalar multiple of an eigenvector is still an eigenvector for the same eigenvalue. So we picked this I1, and so it's not completely clear from the way I've written this that the eigenvectors for these two eigenvalues that come in conjugate pairs should themselves be conjugate pairs, because I don't have them scaled to the same scale, right? If I did that, I would have the first entry be 1 and then see what the second entry would be, because then I would know that they're at the same scale. So I'm going to multiply this one by -I, and so I get I times -I 1, and here I get -I. And that's the eigenvector that I'm going to use instead. Now you see that it doesn't really matter if I multiply this by an arbitrary constant, because it's already being in the general solution. It's being multiplied by an arbitrary constant. So whatever constant that I multiply in or factor out, I can just fold it into that C2. I wanted to make this point because, well, the fact that we can always write the pairs of eigenvectors that correspond to the conjugate pairs of eigenvalues, these are conjugates of each other themselves. So the conjugate of 1 is, of course, just 1, and the conjugate of I is minus I. And this is important because what we started off with was a system. I can just scroll back to that. This system that we started off with, this is completely real, right? There's no complex values anywhere in the statement of this equation. So it's natural for us to want solutions that are completely in terms of real numbers, even though we have complex eigenvalues. So what I want to show is that we can rewrite this thing in terms of just a real solution. Now, first of all, what I'm going to do is I'm going to use Euler's equation, which we've seen before. All right, e to the I theta is equal to cosine theta plus I sine theta. So that's what we end up with if we have e to a complex or to an imaginary exponent. So I can use that to rewrite this. It's going to be C1 times 1 times I. Now I'm going to do a rewriting step first. So this is e to the minus 1/2 times e to the it, right? Just by the rules of exponents. Plus C2, 1 negative I e to the minus 1/2. So that's the real part of this exponential. And then e to the minus it. So that's the imaginary part of it. Imaginary part is a really unfortunate naming for this. Early in the past in mathematics, people were very careful about what they considered to be good mathematics and what they considered to not be good mathematics, and they thought that there was something really fishy about what they called imaginary numbers, and so they only used them as kind of a mental device for coming to a conclusion, and then they tried to reprove it completely in terms of real numbers, and that's hence the term imaginary. Since then, as mathematicians, we've learned that we can sort of YOLO everything and then figure out what went wrong at the end, and it all works out. We call them imaginary numbers, but that's just a historical accident. Okay, so this e to the it should be, so it's going to be multiplied by this whole thing, cosine t plus I sine t. A lot of the secret of the success of great mathematicians far in the past was that they kind of didn't care that the things that they were writing didn't seem to make sense to a lot of people around them. Eventually, we figured out how to make sense out of it. So this should be minus t. And then, what can we do here? By the way, the book doesn't include this. I left something out here, didn't I? 1/2 t. As I often say, it's not important that you don't make mistakes. It's important that you find them. So cosine of negative t, cosine is an even function. So cosine of negative t is equal to cosine t. And then I sine of negative t. Well, sine of negative t, sine is an odd function. So sine of negative t is negative sine of t. This is minus I sine of t. So we've rewritten it in terms of cosine t and sine of t. Now, what I'm going to do is I'm going to just factor e to the minus 1/2 t out of the whole thing. And then I'm going to write this as one big vector. So I'm going to have c1 cosine of t plus c1 I sine of t plus c2 cosine of t minus c2 I sine of t. And for the sake of my sanity, I'm going to move the I out in front. So it's easier to pick out the ones that are imaginary, the imaginary parts. Okay, now I cosine of t minus, sorry, I need the c1. I c1 cosine of t. Now I have this I here times this I, so that's minus c1 sine of t. Maybe I'll write this as minus I c2 of c2 times cosine of t. And then minus I times minus I is negative c2 sine of t. Okay, a little hard to follow. Now, what can I do with this? Minus 1/2 t. I'm going to have the real part, c1 cosine of t plus c2. Let's write it like this. c1 plus c2 cosine of t. And the real part down here is negative c1 plus c2 sine of t. And now the imaginary part. Made a little mistake here in my writing. It should be a c1. So c1 minus c2 sine of t. And then the imaginary part here is double check to make sure I didn't make a mistake. c1 minus c2 cosine of t. Now we have, let's just rewrite this. Let me double check one more time. Yeah. Okay. So if I factor out the c1 plus c2 here, e to the minus 1/2 t. Sorry, just give me 1 second. Hmm. A little lost in my reasoning here. That's the unfortunate thing that happens whenever you the proof is not included in the book. Assume that you can figure it out as you go. So we have our fundamental set of solutions here. This is one solution. This is another solution. And all the solutions are linear combinations of these two. And what I want to show is that I can get two independent solutions in that set that are completely real. Hmm. Oh, got it. Okay. So what we have here is cosine of t minus sine of t plus I c1 minus c2 e to the minus 1/2 t sine of t cosine of t. Okay. So I want situations where I'll get a completely real solution. One possibility is if I make c1 equal to c2, and this part right here becomes 0. And what I'll have is what this right here will become 2 times c1. So I'll call that um, another constant. Let's call it k1. E to the minus 1/2 t cosine t plus minus sine of t. And this will give us, well, any constant multiple of that. This will give us our first solution. So e to the minus 1/2 t cosine of t negative sine of t. Now the other possibility to get a real value right is to say c1 equals negative c2, So this is a different linear combination. And what I will get here is this part will be equal to 0, and I'll get I times some new constant, k2, e to the minus 1/2 t, sine of t, cosine of t, right? Now, because this k2 is an arbitrary constant, I'll just fold the I into that constant. And what I end up with is any multiple of this thing, which is completely real, x2 of t. And so this is our second fundamental solution. So we got our fundamental set of solutions. Now we can plug this into the Wronskian and show that they're linearly independent. But what we did was we formed them by choosing a pair of vectors that are linearly independent, 1, 1 for this one, and 1 minus 1 for this one. Anyway, they're linearly independent. These two solutions are linearly independent. Actually, it wouldn't be, it's not that hard to plug this into the Wronskian. If we factor out the e to the minus 1/2 t from the whole thing, then the matrix that we get is cosine of t minus sine of t. Remember, for the Wronskian for these systems of equations, the columns of the matrix are just the solutions stacked next to each other. So this one would be our second solution, sine of t, cosine of t. And what you see when you take the determinant, this determinant, you get cosine squared plus sine squared, which is just 1, e to the minus 1/2 t, which is never 0. Anyway, I went through all this work. What we ended up getting at the end is if we had taken any one of our solutions, what we would have had was just the real and complex parts of it. So our first one was this. And so what did we have? We had, scoot over here and make some room. 1 times I, well, this was write it out as a vector, e to the minus 1/2 t, cosine of t, plus I, should just copy this down. So I'll call that first one y1. That was e to the minus 1/2 t, 1I, cosine t, plus I, sine t. Um, this is our eigenvector, and then the input to sine here will be our eigenvalue, right? The thing that's multiplied by t was the complex part of our eigenvalue. And when we took the complex conjugate, what we got was y2 of t, e to the minus 1/2 t. We got the complex conjugate of the eigenvector, and we got the complex conjugate of the eigenvalue. And so that sign of something became negative, that sign of that something. And so what we see here is that if we write this, let's write it out as a vector. e to the minus 1/2 t cosine t plus I, the e to the minus 1/2 t doesn't need to be in there. That's cosine t plus I sine t and negative sine t plus I cosine t. And this one was e to the minus 1/2 t. This part right here doesn't change, right? Taking the complex conjugate doesn't change the, that's the real part of the eigenvalue. So we have cosine t minus I sine t and negative sine t minus I cosine t. In any event, what we get is that when we add these two things together, when we add these two vectors together, the imaginary parts cancel out, right? So the sum of these two solutions that have complex parts is completely real. The imaginary part completely cancels out. If we subtract one from the other, then the real parts are the same here. These real parts are the same. And so they cancel out. And we're left with just the complex parts. And of course, we can take, because we're multiplying our solutions by an arbitrary constant, we can just multiply by I and get a real part, right? So we can always do this process by taking just the real part, or just the complex part, or just the, sorry, not the complex part, the imaginary part, of either of these solutions, and take those to be the real solutions. When I say the real solutions, I mean the real number solutions. And this always works out because what we started off with was a system of ODEs that had real coefficients, which means that we end up with a polynomial, a characteristic polynomial that comes from that matrix with real coefficients. The roots, if they're ever complex, appear in conjugate pairs. That gives us conjugate pairs of eigenvalues, which gives us corresponding conjugate pairs of eigenvectors. And so this kind of math always works out. We can always cancel out the complex parts, and we can always cancel out the real parts in this way, so that we get solutions that are just the real part and just the imaginary part. Okay, a lot of work. Let's do another example. I want to do one from the book. Not that one. No, I don't want to do a 4x4 matrix. Stick to 2x2. All right, I'm going straight to the exercises. Wish me luck. Okay, next example. I haven't worked this out before, so if you haven't either, we're all going to be in the same boat. All right, this is our example. How much time do we have? I wanted to give you time to work on one of these yourself and try it out. Anyway, maybe I'll stick around afterwards in case you want to. All right, let's get the eigenvalues and eigenvectors of this matrix. So I'm going to have -1 minus r times -1 minus r, so that's just squared, minus -4 times 1, so that's +4. I'm going straight to the characteristic polynomial. I can get rid of this minus. Let's make it 1 plus r squared, so it's easier for me to think about. You notice what I did there. -1 minus r squared It may be obvious to you, but I did that factorization, right? And so this -1 squared is just 1. So this is r squared plus 2r plus 1 plus 4. That's 5. I'm going to end up with complex eigenvalues. So -2 plus or minus square root of b squared minus 4ac. They nicely gave us a perfect square in the square root there, divided by 2a. So this is -1 plus or minus square root of -16 over 2. So that's plus or minus 2i. Those should be our roots. Okay. So first the root -1 plus 2i. So what do we get for that? Excuse me. We get, well, I'll go ahead and write out the matrix. So -1 minus -1 minus 2i minus 4, 1 minus 2i. We get the same thing because the diagonal is the same. The entries in the diagonal are the same. And we can kind of convince ourselves that these are linearly dependent. Anyway, a1 equals 2i a2. I'll pull that from the second row here. And I get the eigenvector 2i1. Highlight that so we don't lose it. R equals -1 minus 2i. The matrix will be, well, exactly the same, except 2i is getting replaced with -2i. So -2i becomes 2i minus 4, 1, 2i. And I get a1 equals -2i a2. We didn't really need to do it. We knew these were going to appear in conjugate pairs. So the other one would have been -2i1. Actually, getting the second eigenvector we could have skipped entirely because we're only going to use one of them anyway. The solutions that we would get from this are x1 of t is equal to, I'm going to call it x hat because later on we're going to be using x. So x hat 1 is equal to 2i1 e to the minus t cosine 2t plus I sine 2t, right? Sorry, minus I. I wrote minus I. I meant to write minus t. Maybe on this first one, I'll go through all the steps instead of trying to do it in my head. So this is 2i1 e to the -1 plus 2i t. This is 2i1 e to the minus t by using the exponent here. And then Euler's formula for the 2it will be cosine 2t plus I sine 2t. I'm writing it vertically just because I'm running out of room. And then I'm going to write this as its real and imaginary parts. So e to the minus t so -2 sine of 2t. I'm just writing the real part first. plus 2i cosine 2t. So that's the top entry of my vector, and the bottom entry is cosine 2t plus I sine 2t. Now, like I said, we can totally skip getting the second one because we have, in this solution, we have a real part, an imaginary part, and we can choose for those two. I'm going to write 2i, I'm going to write I. It looks weird, but okay. So like I said, yeah, we can skip the second eigenvalue. We know that it's going to just give us the same real and imaginary part, but let's try it out anyway. Up to a constant multiple. So what do we get for this one? X hat 2 of t is equal to negative 2i 1 times e to the minus 1 minus 2i t, which is e to the minus t, and then I'll write it out. I'm going to go through the steps again. Minus 2i1 e to the minus t cosine of negative 2t plus I sine of negative 2t, which is e to the minus t 2 sine of negative 2t minus 2i cosine negative 2t, and then cosine negative 2t plus I sine of negative 2t. Right. So from this one, I get that my real solutions are x1 of t is equal to e to the minus t minus 2 sine of 2t cosine 2t, right? That's the real part. That's e to the minus t times this part, and the other one will be e to the minus t times this part, the imaginary part. So that's x2 of t is equal to e to the minus t 2 cosine 2t sine 2t. Now let's double check and make sure that our other eigenvalue eigenvector pair, our other eigenpair, gives us the exact same answer. We'll move this up here. And so what does this one give me? This gives me x1 of t is equal to e to the minus t 2 sine minus 2t cosine minus 2t. x2 of t equal to e to the minus t negative 2 cosine 2t, sorry, and sine of negative 2t. Okay, so do we get the same thing? Well, on the first one, e to the minus t, 2 sine of negative 2t, because sine is an odd function. We can rewrite this as negative 2 sine of 2t. And cosine is an even function, so this is cosine of 2t. And we see that we do get the exact same thing for x1. And for x2, we get e to the minus t minus 2 cosine of 2t and minus sine of 2t. And well, we don't get the exact same thing here. We get that this is equal to negative e to the minus t 2 cosine 2t sine of 2t. So we get that this one is the negative of this one, but that's okay. It's still a fundamental set of solutions because this is always going to be multiplied by some arbitrary constant anyway. And so doesn't matter. That -1 in the front here, we can just fold into our arbitrary constant that's going to be multiplied by it anyway and ignore it. And so yes, we do get the same fundamental set of solutions from these two. So when we have a complex pair of eigenvalues, it may be a little bit of a pain because you have to remember the rules of exponents and Euler's formula for turning it into sine and cosine, all of that stuff. Or you can just memorize how it turns into that. On the other hand, we have two distinct eigenvalues here, but we only have to do the work for one of them. So we're kind of cutting our work in half in a way. So in that sense, it's a good scenario. Works out well. Now, let me kind of rewrite these things so that I can scroll all this off the screen. I'm going to take it one step further. And x2 of t is equal to e to the minus t, 2 cosine 2t, sine of 2t. And that extra step is that I'm going to turn this into an initial value problem. So our initial ODE was -1, 1, -4, -1. Say minus instead of negative, one less syllable. And let's say, what do we want our initial value to be? Let's say we want our initial value, x of 0, pick an arbitrary one. -1, 3. Why not? That one last step is solving this initial value problem. If you are ever faced with this situation, what would you do? Well, we want to find, let's write out our general formula first. C1 e to the minus t minus 2 sine of 2t cosine of 2t plus C2. So this is, if there were a question asking on the exam for the general solution to this homogeneous system of equations, this is what it would be. So what we're trying to do is we're trying to find C1, C2, so that x of 0 is equal to x of 0, which is C1 times e to the minus 0, so that's just 1, minus 2 times sine of 2t. So minus 2 times sine of 0, which is 0. And then cosine of 0, that's 1. So there's our first part. And then C2 times e to the 0, 1. 2 cosine 2 times 0. That's 2. And that's 0. So we want to find this so that it's equal to -1, 3. And if you watched the lecture from yesterday, you'll see I did some examples of this for the distinct real values. In this case, it's actually even easier. Now, what would I have done if these were distinct real values? Oftentimes, we end up with vectors here that don't have a lot of zeros in them. Let's do it in that way. 0, 1, 2, 0, the way that I did it yesterday. So this, I'm looking for something multiplied by this vector plus something multiplied by this vector to give me this vector. This is just can be rewritten as a matrix vector equation. So we take those vectors and make them the columns of the matrix. C1 and C2 are this vector here, and we're trying to get it equal to -1, 3. So we can solve this by computing the inverse and multiplying it on both sides. Good practice, so let's do it. We call this thing, we had a matrix A before, so let's call this one B. So B inverse is the reciprocal of the determinant. The determinant will be 0 minus 2, so -1/2, times, swap the diagonal, swap 0 and 0, we get 0 and 0, -1, -2. And so if I want to get C1 and C2, I just do this matrix multiplication here. What I get is C1 is equal to -1/2 times 0 minus 6. So -6 times -1/2 is 3. And C2 is equal to -1/2 times -1 times -1. So -1. And we get that our specific solution is 3 e to the minus t -2 sine of 2t cosine 2t minus 1/2 e to the minus t 2 cosine 2t sine of 2t. Now in this case, actually we didn't have to go through all that work. I was just doing it as practice for this scenario. In this case, we can just look at this system right here and see, or this equation right here, and see that we're going to have C1 times 0 plus C2 times 2 is equal to -1. And C1 times 1 plus C2 times 0 is equal to 3. And we don't even have to go through the work of computing the inverse. We have C1 is 3, and we have C2. We just divide both sides by 2. So it works out. We could have done a much easier thing in this case, get the specific solution. Anyway, it's 11:22. I can stick around and do another example if you want me to. How do you feel? If you end your Zoom call, I will automatically know how you feel. If you don't, and you haven't, okay, I'm doing another one. One more. I've got to live my life at some point. X prime is equal to 2, 1. Double checking to see everyone's still here. -5, -2, x. All right. Examples are always helpful. So once again, I'm gonna do a lot of mental shortcuts and just jump straight to the characteristic polynomial. So it's going to be 2 minus r times -2 minus r. Quite easy in the 2 by 2 case. I did an example yesterday of a 3 by 3 case. So that's something nice to see. Much harder in that case. So minus -5. And this will be equal to r squared. I want to do a nah. Let's just work with it as is. So minus 2r plus 2r, and then -4 plus 5 plus 1. Okay. Now in this case, we don't have to use the quadratic formula. We know that the roots are going to be plus and minus I. It's going to be the square root of -1. So either I or -I. All right, now to get the eigenvectors, we will have the matrix 2. I'll choose the minus I because it's nicer to write pluses. 1 minus 5, -2 plus I. And really, I only need one of these rows. So I'll go with the, you know what? Actually, I changed my mind. Go with minus I. Because this bottom one, so this will be subtracting positive I from the diagonal. This bottom one, what do we get? We get A1 is equal to 2 plus I A2. And we get as our eigenvector 2 plus I 1. So the eigenvalue for this one was when we were subtracting away positive I from the diagonal. So this is our eigenpair, the eigenvalue and the eigenvector. And we get from this that I'm going to write the solution as x hat of t is equal to. Now this is a solution. This is one of the general solutions. What am I trying to do? 2 plus I 1 e to the I. This is 2 plus I 1 cosine of t plus I. Sorry, I t, not just I. Cosine of t plus I sine. Right, we have our eigenvector, and then we have e to the eigenvalue times t. Now, there's no real part of the eigenvalue this time, so there's no exponential decay. Right, in this last one, we had a component of either exponential growth or exponential decay. Right, we had this e to the it, so our solutions will be oscillatory if we look in the x1, x2 plane. They'll kind of spiral inward towards the origin because we have this exponential decay. As time grows, our solution is going to shrink towards 0. In this case, we have nothing like that. So this is purely oscillatory. We're going to have, if we look in the phase plane, x1, x2 plane, then we're just going to have ellipses. All right. Anyway, I want to get my two fundamental solutions. So I'm going to split this up as a real and imaginary part. So let's say we want 2 cosine of t, and then, yeah, let's just do it like this. 2 cosine of t plus 2I sine of t plus I cosine of t plus I times I, so negative sine of t. And this one is just cosine of t plus I sine of t. Now collecting together my real and imaginary parts. Two cosine of, I left out something, didn't I? The vector. No, I multiplied it through. This is a vector. Never mind. 2 cosine of t minus sine of t cosine of t. That's my real part. My imaginary part is 2 sine of t plus cosine of t sine of t. So what do I get for my general solution? X of t is equal to c1 times 2 cosine of t minus sine of t cosine of t. Right? This is my x1. My x2 be c2 2 sine of t plus cosine of t. plenty. So of course we can recover x hat by subbing in 1 for C1 and I for C2. Anyway, there's our solution. And we turn this into an initial value problem by tacking on an initial value. X of 0 is equal to 0, 0. Say both of our weights in our system, both of our masses in our system start at the origin at their equilibrium point. What happens? Should anything happen? Maybe it just sits at 0, 0. Let's find out. That's what you would think if both of the masses start at their equilibrium position. They're already at equilibrium and they don't change. So what happens? We get C1 times 2, 1 plus C2 times 1, 0 equals 0, 0. Maybe this is a good point for me to inject another definition. So we have a linear combination of two vectors here is equal to 0. If the only linear combination that we can make of two vectors that's equal to 0 is the combination where we set this one equal to 0 and this one equal to 0, then these two things are called linearly independent. This is really what we mean when we say the definition of linearly independent. The only linear combination that we can take of these two things that makes 0 is just 0, 0. So if we look at this, are these two things in fact linearly independent? There's a lot of equivalent ways that we can try to figure that out. One way is to actually form the system. 2C1 plus C2 is equal to 0. And 1 times C1 plus 0 times C2 is equal to 0. We got C1 is equal to 0. We plug that in here for 0, and we get C2 is equal to 0. And in fact, we have solved this linear system of equations to show that the only linear combination of this vector 2, 1 and this vector 1, 0 that gives you 0, 0 is multiplying them both by 0. Now, this is entirely equivalent to what we did before, which was form the matrix. The matrix would have been this. The vector would have been this. And this would have been the whole matrix vector equation. And now what are we doing? Well, if we try to solve this by finding the inverse of the matrix and multiplying it over the other side, we're saying we're finding some vector, multiplying it by 0, we get 0, and so that should give us C1, C2 is equal to 0. The only possible thing that could go wrong is if the determinant of this matrix is 0. We look at the determinant of the matrix. 2 times 0 minus 1 times 1, which is -1, and now we're getting some deep math here, not 0. The determinant is not 0, which means absolutely nothing will go wrong. That means that these columns of this matrix are linearly independent. Okay, that's your little preview of Math 322 for today. And was I right? Is Math 322 actually a required course for engineers? I think it is, isn't it?
I know I don't have to take it. I don't know about Sarah.
You don't have to take it.
Mm-mm.
You should have to.
I just know I have to take a statistics class later on, but I don't think I have to take another math class. I think like this is my last one.
You mean you don't get to take another math?
I don't get to. Yeah, we'll say that.
322. I have to. I mean, calculus is very important. All of science is basically written in the language of calculus, right? So if you look at any physical system, all of the governing equations of that system will always be written in terms of differential equations. So that's sort of like the purpose of all of the math that you've done throughout your entire life, was to get you to this class right here. But I think that in the sciences and engineering, probably at least as important, maybe even more important, is an understanding of statistics is extremely important, and linear algebra. Linear algebra is also fundamentally important in understanding science and engineering. So although you're not required to take it, I do highly recommend that you do the class because it's an interesting and very important thing to be able to understand. Anyway, that's my wisdom that I'm passing on for today, and I'm going to call it. So have a good day. I'll see you Monday. I'm going to go ahead and tell you that repeated roots or repeated eigenvalues is not going to be on the final exam. I'm going to try to go over it a little bit on Monday and do an example, but mostly I'm going to just stick to whatever kind of review you want to do. So the final exam is going to be about half and half series solutions and systems of linear differential equations. So we can split our time amongst those two things for Monday and Tuesday. Also, the final exam will be open Monday and Tuesday if you want to just go ahead and knock it out. Anyway, I'll call it there. Have a good day. Have a good weekend.